In this problem, we have a sliding coin within a frictionless plane, a constant force with magnitude of 3 newtons and directed at a counterclockwise angle of 40 degrees with respect to the positive y direction is applied to the coin. The question is, what is the work of the force as the coin slides from the point A with coordinates 0, 0, that is the origin of our coordinate system, to a point B with coordinates 3, 4. Here the coordinates are given in the metric system, so we don't have to worry about converting of units. Let's start with our coordinate system and see if we can actually draw a diagram of the problem or the situation so it can help us visualize what is happening. Here is the XY coordinate system and the force F, which is in a counterclockwise direction at an angle 40 degrees with respect to y-axis. So be careful. Many problems give the angles from the positive x. In this particular problem, we actually have the angle measured from the positive y direction. Then we have the coin starting at the origin at point A, 0 with coordinates 0, 0, and going to a point B with coordinates 3, 4. This will be our displacement, delta L. Now let's look at the formula for the work. The magnitude of the force is constant, it doesn't change. The angle between the force and the displacement is also fixed. So we can use this simple expression for the work, which is F, the force, the magnitude of the force times the magnitude of the displacement times cosine of the angle between the two. Immediately we can replace F with 3 newtons because that is what the problem tells us. So let's look at the delta L. The first thing we notice is this highlighted right angle triangle for which delta L appears to be the hypotenuse. The sides of that triangle are actually 3 and 4, which are the coordinates of point B. So the x-coordinate 3 will be one side, and then the y-coordinate YB equal to 4 will be the other side. With that information, we can apply the Pythagoras theorem here to determine what is the hypotenuse of this triangle, which will turn out to be equal to the displacement delta L, which we need for the formula for the work. So here we have delta L will have to be equal to square root of the sum of the squares of the two sides. xb squared, which will be 3 squared, plus yb squared, which will be 4 squared here, and that gives us 5 meters. Well, I chose a very nice triangle here. Anyway, one of the classic Pythagorean triangles. Anyway, so going back to the work, now we can replace the symbol for the displacement with its numeric value. So far we have that the work of that force will be equal to the magnitude of the force, 3 newtons, times the magnitude of the displacement, 5 meters, times cosine of the angle between the two. I have marked here this angle as theta. Before we tackle the question about what theta is, let's look at that highlighted right angle triangle again. This angle here is alpha, and we see that for the highlighted triangle, tangent of alpha, by definition, will be the opposite side to the adjacent side of that right angle triangle. For our problem, that will simply be the ratio between 4 and 3. Arctan of 4 over 3 gives us for the value of the angle alpha to be 53.13 degrees. I have kept one extra digit here because I don't want to accumulate rounding errors by the time I reach to the final answer of the problem. Now let's look at this angle beta, which is the complementary angle to alpha. In other words, alpha plus beta add up to 90. That means beta here is going to be 90 minus whatever we calculated for alpha, so that means that beta has to be equal to 36.87 degrees. With that, we are ready to look at the total angle, the angle between the force and the displacement, which is theta here on our diagram. And we can see that that angle is simply the sum of the 40 degrees that are measured from the positive y, plus another extra angle there, which is equal to beta. Or that will be 40 plus 36.87, the value that we determined for beta. In other words, the angle between the force and the displacement will be equal to 76.87 degrees. Now I'm finally ready to calculate what the work of the force is here. I'm going to have the magnitude of the force, 3 newtons, the magnitude of the displacement, 5 meters, and cosine of theta, the angle between the two, which turns out to be 76.87 degrees. And that gives me, for the work done by that force F on the coin as it slides from point A to point B, to be plus 3.41 joules.